Hi everybody. Today we're going to talk about a skill every malware analyst should have, the ability to automatically label obfuscated APIs that are resolved at runtime. We're not going to go into the background of how to identify the functions that resolve these APIs. We did that in a previous video, how malware resolves APIs by hash. Today we're going to focus on the next steps, what you do after you identify that resolution function. Primarily this, how to determine what the obfuscated API is, and then secondly, how to transfer that resolved API into a marked up disassembler database for analysis. We're going to spend a little bit of time on the academic background, and then we're going to walk through 3 examples to demonstrate the skill in different scenarios. Let's go into a little bit of the background. We want to know basically why malware obfuscates APIs. It does this primarily for 2 reasons. One is to avoid AV detection, and the second is to slow down malware analysts. If the AV scanners can't identify the APIs that are used, it means they can't flag the malware as suspicious just based on suspect API usage. And similarly for malware analysts, you really determine the capability based on API usage. That does the heavy lifting. So if the APIs are obfuscated, then you have to go through the work of determining what the obfuscated API is. And if you don't have enough background or skill to do that, you won't be able to determine the capability. Even if you had the background, but you don't have tools to work with it, it can take you a lot of extra time and may just make it infeasible for you to analyze a file. So it's a relatively common technique that you come across, and so having a way to quickly and efficiently deal with it is really a must for any malware analyst, and that's what we're going to talk about today. So our goals is to quickly identify and label all API calls so that functionality can be determined. We have a concern or two about this though. We don't want to modify the binary, we just want to annotate it. There are methods where you can resolve the APIs in debugger and then kind of take a snapshot of that memory with the resolved APIs, but that creates a dirty binary with modified bytes. If you only modified the API bytes, it might be okay, but you may have modified other bytes, like maybe strings got decrypted, other actions got performed, and so then you run into the risk of having unintended consequences because you have a dirty binary, and we'd really want to limit that because if you're analyzing a file and it does something odd, you don't want to have to be wondering if it's because it's something you did versus something that malware is doing suspiciously. The second reason is really the most important one, and this is for building YAR rules. If you build the YAR rules based on the bytes you find in the binary, you really don't want to have modified bytes because you run the risk of making YAR ruled on those modified or dirty bytes, and then your YAR rules just aren't accurate for the clean file that would run across. So there's 2 approaches we can take for resolving these APIs and annotating it. You can do it statically through scripting or dynamically through a debugger. They both have pros and cons. Scripting takes more experience and education and time to build up front, but the more times you have to run it on variants, the more your time is spread out. So basically it's more upfront time, and then every time you rerun it, it has usually you can run it really quick, and so you have a decreased time the more times you need to do it. Resolving it through debugger is the exact opposite. You can usually resolve the APIs for one file relatively quickly, but you don't have any time savings for doing it on more files. So if you have to run dozens of different variants or just the same sample over and over again as you get it collected, instead of making that time upfront and then decreasing time over the length of the samples, you basically have to repeat the process over and over again, and you don't save any time. So we want to basically use a method that comes in between those. So we're going to take the best of both worlds. We're going to use a debugger to resolve the APIs in memory, and then I'm going to provide some tools that are going to dump those APIs into a file and then transfer it into a Ghidra database. So we basically get the power of the debugger where you don't need to spend a lot of time to reverse engineering hashing or obfuscation algorithm, but also the power of scripting to transfer those into a clean database. This way, every file you do will take a little bit of time, but it won't take a huge amount of time like it would if you're just dynamically resolving the debugger and then manually copying those names over into a database. The scripts we provide will work with any debugger. It just has to dump it out of memory, so whatever your debugger of choice will be fine. We're going to use X32 debugger for our videos. The script works just with Ghidra, but the script is relatively simple, so you could port it over to IdaPro or Cutter or any other disassembler relatively easily. We only have a few requirements. The function that resolves the APIs has to be able to get called. So if it's on the main code path and the file doesn't exit when you run it, you don't even have to go in the debugger. You just run the file and dump the kind of labeled IIT out of memory. We're going to show one example for that. The other thing is we need to basically you don't have to worry about changes to the file. We're going to run the file in debugger and output the resolved APIs with a relative virtual address, and they'll get copied in a brand new database. So that means we don't have to worry about the dirty bytes where we're building our YAR rules. There's two common variations that we want to talk about and that we're going to deal with. The first is the most common. This is where the resolved APIs are stored into global addresses, usually the .data section. That means the API is stored at the same address in every file, so it makes scripting relatively easy. This is what the Ghidra script is going to work with. The second case is less common, and this is where the resolved APIs is stored in a structure in the stack or a heap somewhere. That means every time you run it, it could be a different address, and so there isn't a script that will transfer it off easily, but there's some workarounds that most disassemblers will help you with, and so our tools will kind of build a intermediate form that the disassemblers can handle, and it'll take a little bit of manual work, but still far less than if you're doing this by hand. So we have 3 tools we're going to provide. All the tools we provide are listed in the description of the video and can be downloaded off of my GitHub page. So the 2 tools to dump the APIs out of memory in the debugger are going to be this dump labeled API structure and dump labeled IAT memory. The dump labeled IAT memory is for when you're dumping it and they're stored in global variables. If they're stored in a structure, then we're going to dump this labeled API structure. The third tool is a script, this labeled dynamically resolved IAT entries. This script really only works with the dump labeled IAT memory, and this is where it's going to read in the output of this dump labeled IAT memory, and it's going to transfer all those resolved API names into the Ghidra database at the global variables where they're resolved to. It only works at one script because those are the only ones that have hard-coded addresses. And if you dump the API structure out of like a stack or heap, it has a different address, so there's not really a good way to script that. Alright, so that's really all the background we need to talk about. The next step is just to work through some examples. All these examples are listed in the description and can be downloaded from Malware to practice on your own. Let's go into our example 1. So I'm going to type G to go, and I'm going to go to address 403.250. I'm going to open up my graph view, just to make it a little bit easier to see this. And then as I scroll through here, I'm going to select my calls, and I see immediately I have 2 calls to that variable, so the global variables. If I keep on scrolling down, I see more calls to global variables. So this is the labeled IAT in the global variable scenario I talked about. So the APIs will always be resolved at the same address or stored at the same address. Like in this case, it's at address 4166 Charlie 0. So it's not going to change except for ASLR. That means it's going to be their simplest case. So you always have to do a little bit of reverse engineering potentially, or you could just test it out to see if it works. So let's go into our imports. And so if I open up the imports here, I see it has kernel 32, so I'm going to select that and expand it out. I see it's got a number of kernel 32 imports. Then it has shell user 32, ws32. We see ws32 only has a couple functions in it. So it looks like it has some imports, but because it has the calls to global variables, we know it resolves more imports dynamically. So this is the very simplest case where the function that resolves the imports is on the main code path, and the file doesn't exit memory if you just run it. So we're actually going to show the case of, without even doing any reverse engineering, how you can just test this out and see if it works. The first thing we need to do is I want to show what inputs we're going to need for these tools. So I'm going to open up a command prompt, and I need to run it as administrator because we're going to be reading process memory. So run as admin. And then I'm going to change directory to my demo folder. And I'm going to look at this dump labeled IAT memory. So if I look at the usage statement, I see that I'm going to need the target PID, the target module base name, and the output file name. So basically we're going to read this PID, and we're going to read the memory of this module base name, and we're going to parse it looking for all the addresses for any resolved APIs. Once it finds a resolved API, it's going to output that to the output file along with the RVA. We do a relative virtual address instead of a virtual address, so that when we're copying it into the Ghidra database, we don't have to worry about ASLR. It'll basically take the base that Ghidra has, and it will update the RVA for that full virtual address, and then be able to write or comment the global variable that way. So I'm going to go ahead and copy this example1 file name because I'm going to need it to put in the command prompt. And when I double click this to run this, it's actually going to move itself, so it's going to disappear out of this folder, but that's not a big deal here. I'm going to double click it to run it. And then let's look at our process hacker. We see in our process hacker, we had this example1. If we see if we just sit here, it's not exiting out. So that's a kind of best case. Maybe it's inside of a loop and it's doing something, but it's not exiting. So we can just try to read the memory without doing any investigation beforehand and see if we can find a labeled IAT in there. So I see my PID is 3256. So I'm going to run this tool. So a PID is 3256. I'm going to right click to paste in my module base name. And then I'm going to call the output example1.txt. And I'll hit enter. And now let's go ahead and open up this example1. And let me zoom this in a little bit, make it easier. So we see we have a lot of APIs starting at this relative virtual offset of 10,000 hex. So as I scroll through here, I see this still in the 10,000 range. And then I see it jumps up to the 1660 range, and I resolve load library again. So this is probably the dynamically resolved API. So this original 1000 or 10,000 hex is probably the imports that had just an import address table. And now we have our dynamically resolved import address table, starting with load library, get proc address. And if I keep on scrolling through here, I see I have some networking functions that didn't have in my imports. I have the listen, I have the accept, I have the connect. And so that gives me the more confidence that's the dynamic resolved APIs. So you can see just by trial and error, I can check it very quickly and don't even have to reverse engineer it in order to find the function that loads the imports. Let me close this down and go back into Ghidra. And now I'm going to open up my script manager. So I hit the little play button. I need to add my scripts. So I'm going to go to this little paper symbol here, the 3 lines, and open that up. And hit the green plus button to add my script directory. And it's in my demo folder. So I'll go ahead and hit OK. And now once I added my scripts directory, they will show up under AGDC services. So it's going to be this label dynamically resolved IAT entries. So I'll hit the play button again to run the script. It'll take a second to come up, and it's going to ask me for a file. I basically just point it to the output file that came from the dump labeled IAT memory. Then go to the C drive, and then the demo, and then I'm going to select example1.txt, open up, and then it's going to run. While that's running, let me go ahead back to my graph view just to make it a little bit clearer, and we see it labeled my call here with get file attributes. So now I can see as I'm scrolling through here, I have the get file attributes called twice. I have create file called twice. I keep on scrolling through, I get file time, set file time. So before there would be no way to analyze what this function does. Now I can scroll through here and I have the APIs. So I can see get file attributes has 2 different arguments. This one is ESP plus 30, ESP plus 240. So getting file attributes of 2 different files. I call create file, it looks like with a different argument. So I'm opening up 2 separate files. And then I'm doing a get file time and a set file time. Close my handles and exit out. That looks like I'm probably doing a good chance of timestamp functionality. I did look at a little bit closer to verify, but just from the quick triage, it looks like a timestamping. And so you can see I didn't have to reverse engineer to find the load imports function. All I did was a little bit of trial and error, and now I can analyze the file. So that's the very simplest case that we're going to have. So let's go ahead and close this down. Close down the script directory. And this example1 I can close out. I don't need to save that. Alright, so let's go to our example 2. So our example 2 is going to be a little bit more complicated example. So I'm going to hit G to go. I'm going to go to address 40388F. Now open up the graph view to view this a little bit easier. And then I'm going to scroll through, and I see again, I call to a global variable, and I see some are resolved, and then some are global variables. So they, just like before, they use some from the import address table, and then some from the dynamically built import address table. So I'm going to use the same tools, but this one takes a little bit of reverse engineering before we can use it. I'm not going to go over the reverse engineering aspects because this video is just about how to use the tools to speed up your process. But I basically did some initial triage analysis, and I found where the functions were that resolved a import address table. So in this case, I'm going to type G to go. I'm going to go to 403 echo 3 Bravo. And this is the function that does the load imports. I'm going to select it, hit L to label, and I call this load imports. The other thing I need to know, so when I did the reverse engineering, I found out that this takes an argument, and the first argument is basically module handle of the import that it's going to resolve. And it's called several times. So I can see if I do Control Shift F to open up the cross references, we have this called 5 times throughout the code. So if I just double click this and run, it basically exits out. It doesn't resolve the APIs and save in memory. That's why it's a little bit more complicated. I don't have to worry that these load imports function isn't on the main code path because I can change my EIP in order just to run these because they're basically standalone functions. And most of the time we have a load imports, they work that way. So it's not a big deal that not in main code path, and we'll show you how to deal with it. The one other thing I needed to do is if I go to the entry, as I found if I go into this first unlabeled function, and then I scroll down, this function at 2177, I need to get past that function in order to initialize some global variables that are used throughout the rest of the program. And so basically I just need to run down the main code path up to this point, and then I can change my EIP to the functions that resolve the imports, and they'll be resolved in memory, and then I can dump them out. So I'm going to basically just demonstrate that in X32 debugger. So we'll take example 2, and I'm going to go ahead and copy the module name because I'll need that for the script or the tool. I'll pull this over X32 debugger. Alright, I'll hit F9 to get in the main module, and then I'm going to step up to the first unknown function. I'll F7 to get into it. And now I'm just going to step over the functions until I get to the one that was at 402177. I step over that, and now everything should be, all the global variables should be resolved in memory, and I can go directly to the functions that load the imports. So I'm going to go back to my Ghidra database, and I'll go to the references. So I'm going to do this for each of these 5 references. So I'm going to go down the order. I need to go to address 401 Charlie 7 Bravo. So I will go Control G 401 Charlie 7 Bravo. And then I go up because I know I needed the argument. So I'm going to select the first argument. I'm going to right click, and all I do is set new origin here. This changes the EIP. And then I F8 to step over it, and now whichever module this is resolving, the imports are all resolved in memory now. I'll go back to my cross references and do the same thing for the rest of them. So I'm going to go to 402235, so Control G, 402235, go up to the argument, right click it, set new origin here, and then I'll F8 to resolve that memory, and then check my next cross reference. 403 F56, Control G, 403 F56, go up to the first argument, and here I'll use a shortcut key, it's Control star, that changes my origin, then F8 to step over. Now for the fourth one, 409819, Control G, 409819, up to the argument, hit Control star, then F8 to step over. And then last one, 409947, Control G, 409947, up to the argument. I can do the right click, set new origin here, and then F8 to step over it. You see how even though these weren't on the main code pass, it still only took me a few minutes to resolve these manually after the reverse engineering. That means if I were to do this by hand, I'd have to go into the import address table where they're resolved in memory, copy the names out into the clean Ghidra database. It would take me, I don't know, 15-20 minutes to do that for all these, as opposed to a couple minutes. So even though if I built a script to do this all automatically, it might be able to run in seconds on all the variants. This will only take me a few minutes every time I run it. So even if I do this for 20 different copies, it's still going to be a pretty quick situation. All right, so I can close this down. All right, so now we need to do the script again. We're going to do dump labeled IT memory. Our PID, scroll down to the bottom here, is x32, is 5112. 5112. I'll right click because I saved off the module name before. And we'll call this sample2.txt. Hit enter. And then we'll go ahead and close down x32 debugger, because I don't need it anymore. Then we can see our example 2. I'll open it up. Zoom this thing a little bit. And we see again, these first ones are probably the actually import address table from the compile time import address table. I scroll through and I see it jumps from the Bravo range up to the 12 range. And that's probably where we have our dynamically built import address table. And you can see we have things like find first file, read process memory, create process. So we get a lot more functionality now. So I'll go back to my Ghidra database. Go to my scripts directory. Then the AGDC services. And then I'll hit the play button to run the labeled dynamic resolved IET entries. It'll take a second, and then I select my example 2, open up, and while that's running, I'm going to go to my graph view. Then let me go back to the part where we demoed before. So I'll hit G to go. I'll go to 40388F, and then I'm going to scroll down. And I see here we have create tool help 32 snapshot. Module 32 first, so I know I'm reading through modules of a process. Has some unknown functions. Module 32 next. And so now I could start analyzing this because I have the APIs resolved. So that's all there to it. That's one of the more complicated examples because the file doesn't stay open in memory and the APIs or the functions that load the imports are spread throughout the function. But once you do a little bit of reverse engineering, identify those functions, you can see it's, only takes me a couple minutes to go through and label the APIs for any variant after this fact. Let me go ahead and close this down. Close down my scripts. Now close down example 2. Alright, so now we have one more example to do. This one we're going to do the dump labeled API structure. So I'll hit enter to see the usage. So in this case, let me go ahead and show this one. So I'm going to type G to go, and I'm going to go to 40 Bravo F Charlie 0. Then I'll open up my graph view to make it a little bit easier to see. So I'm going to scroll through here. And now we see a call here to ECX. ECX comes from a register plus 14 Charlie, and we see the register looks like it comes from this function. Let me double click here. And once this function redress, we see all we're doing is getting a global variable. So I'm going to hit out of label. I'm going to call this get IT struct. And that's all we're doing. So I hit Alt left to get back. And this is the third case we talk about where we're building an IET structure in heap memory. So we basically have a global variable. In fact, let's go to it again. Actually, yeah, we'll double click this. This global variable is going to have a pointer to heap memory, and that heap memory is where we're going to store the IET structure. So we'll hit Alt left to get back. So we're going to get that IET structure. We're going to go to some offset inside the structure, move that into ECX, and that's the API offset we're going to call, or the address. So just like before, we have to do a little bit of reverse engineering work for this because they're in the structure. So I'll hit G to go, and my function, actually I can just go to entry. So this function is inside the first function of the address entry point. If we double click this, we'll give Ghidra a second to redraw it. And this is going to be the load imports function. So as this loads up, we see the satellite view in the bottom right, a big, long, huge function that's basically almost a straight line. A lot of times when you see that, that's a kind of load imports function because there's no real control flow. It's just a straight function where you're resolving all the imports. We can also see we're passing hash function into some functions. And if I scroll through here, so I see this is the part where it really looks like the resolve IET. I have a repeated function. We pass a hash into it. The result goes into, in this case, a register, which comes from the same global variable, plus an offset. So we do the base plus 4 plus 8 plus Charlie. That means this is our pointer to our IET structure. We move that in ECX, and this is the basically going to be a get proc address by hash, because you see we're passing probably a module handle and then the hash of the function we want to resolve. Again, we're not going to go into how to identify this function because that was done in the previous video, but definitely check it out if you're not familiar with that so you can recognize this easily. So all we need to know now, we're going to need to know where this memory is on the heap. So we have this hard-coded API that we can go to the address, and then we can see where it points to. That address it points to is going to start at offset 0, and then it'll go to 4, 8, Charlie, and I'm really just going to scroll all the way to the bottom of this function to see where it ends, because I need to know the ending location to dump out of memory. And I can see I had the same global variable, and I go to offset 25 Charlie. That means from the start of this structure to plus 25 Charlie, and then plus 4 bytes for the length of this pointer, or 260, is how big our structure is in memory. If we go to our executable to dump this memory out, we see the name target PID, but because we need to dump this out of like heap or stack memory and not a module, we give it a starting address and an ending address. So we're going to read the starting address out of the debugger, and then we'll just use a calculator to get the ending address, basically the start plus 260 hex. Once we have that, we need the output type. That's going to be either -S for a structure or -E for enum, and then the output file name. I'll show you what both those look like, but all we're creating are header files with an API structure or an API enum, and most disassemblers, Ghidra and IdaPro, can import those header files and parse them, and then it'll build the either structure or enum for you. So for Ghidra, we're going to use the enum because that's how you label these, and we'll demonstrate it. If you use IDA, then you'll probably use a structure. It just depends on the tool. They each do it a little bit differently. So now that we have the basic methodology, let's go ahead and look at this in debugger, and we'll show you how it works. So I'm going to run example 3 in x32 debugger. This one has ASLR on, so we're going to do a little bit of work. I'll hit F9 to get into the address space. And then remember, if we step over this first function, that was the load imports function. So let's look at our module base. We're at 13 delta 0000. So that's our virtual base. We're going to need to add to that RVAs to calculate some of this stuff. Let's go back to Ghidra. And we see our global variable here. This is going to be the pointer to the heap memory that stores the API structure. This is the address 410178, but our base address is 400,000 hex. So our RVA is 10178. So we're going to add that RVA to the image base in the debugger we have. So we'll add 10178 to 13 delta 0000, and we'll get the address of this global variable in memory. Let's go demonstrate that. I'll go down the hex view, Control G. So I'm going to do 13 delta 0000 plus 10178, I think it was. Let me double check. 10178, that is correct. And hit OK. And now you see we have a pointer in memory. And remember, this is little endian because it's a pointer, so we have to start from the right to left. So if we go into the top view here, I'll hit Control G to go. And we go to this pointer in memory. So right to left, it's 1, 5, 3, delta 3, 5, 8. You hit enter, and you see it looks like code. But if I select just a range of here, because we know this is an import address table, I'm going to right click and go to analysis, and then treat selection as, and I'll do a D for D word. So I'll select that, hit OK, and you see how these are resolved addresses, API addresses. We have sprintf, string car, string delong, etc. That means we have the start of our API structure, and now we need to calculate the end. We're going to open up a calculator, and we'll do this in hex. So our starting address will read this off the memory. So it's 1, 5, 3, delta 3, 5, 8, and plus 260 hex. Remember, that was how big the structure was. This can go from, this will be our ending address. Let's put that all inside of our tool now. All right, so we're going to dump labeled API structure, and then we gotta look up our PID. So this PID is 7984. 7984. We need our starting address, so let's go back to x32 debugger. And then I'll read this off the hex view hex dump in the bottom. Remember, little ending, so 153 delta 358. Then we need our ending address. We'll get that from the calculator. This is 153 delta 5 bravo 8. Finally, we need a -e for enum, and then we're gonna call this example 3, and we'll call this struct. Actually, no, I'll call this enum.h. And we're gonna do the same thing for the structure just to show you what it looks like. And -s for the structure, and hit enter. Let's go ahead and open those up so we can see what they look like. So I'm going to select both of them, and this time I'm just going to open up in Notepad++. And I'll zoom in so it's a little bit easier to see. You can see here this is our enum, so it's going to always be called API enum. You can see it has the APIs and then what the offset is, and it's just an enum header file. The structure is the same way. It's got the API struct, and then it'll be the dword. If there's individual bytes in between here, it'll call it like field underscore the RVA with a byte. So just a note for the structure. So these are built to work in Ghidra because that's the tool we're using for these videos. If you use these in IDA Pro, it's going to be a little bit different. Unfortunately, Ghidra and IDA Pro both take different stances. Ghidra, for the structure, the size fields had to be lowercase. IDA Pro is the opposite, it has to be uppercase. So if you want to use this with IDA Pro, you just need to control find, replace all dwords or bytes with the uppercase equivalent. So unfortunately, just the tools weren't consistent, and so you have to do a little bit of a workaround depending on what tool you use. Let's close this down. Let me go back into Ghidra. Alright, and I'm going to go to here, File, and they have this parse source. And again, IDA Pro will have a similar function for loading a header file. I hit this green plus button to add in my header file. I go to C drive and demo. And I'm just going to load the enum because that's the only one we need for Ghidra. Hit OK. And then I'm going to parse the program and just select all the defaults. So continue, continue. And this will take a second because it's a relatively large enum that's pulling in. So it's going to parse it. And then in this bottom left, the data type manager, it's going to add it into there. And because we know it's called API enum, I can go to the filter and just type out API enum. And then I'll load up and I'll show you what it looks like. And close down this parse header. I'll just double click this. And then we have it opened up. So we can see here, make this a little bit bigger. You can see it's the enum that we saw. So it goes from 0 up through to 5 Charlie for the last API. And you can see, again, it took a couple minutes to do this. Where imagine if you had to go build this enum yourself, that would take, probably on the order of hours just with that many APIs that copy and paste or retype over, or at least, half an hour to do that. So again, it's not as quick as if we would have built a script to do this when we run variants, but it might only be 3 or 5 minutes to run this for every variant. So it's really a good middle ground. Let's go ahead, close this down, and show you how to use it. Let me open up the graph view. I think it might already be open. So again, Ghidra and IDA Pro would be a little bit different. In Ghidra, in the graph view, when we see a structure plus an offset, you can't actually apply the structure unless it's applied to a variable. For the register, you have to apply enum. So I can right click this, and then I'm going to go set equate or the E for a shortcut. And it's going to pop up all the enums that have that as or in my database. I'm going to search for API enum because I know they're all in there. And you can see is get module file name exw. Hit OK, and then it will update the name for us. So I can look at other ones too. So you can see here, let me see. Let me go back to, I'll type G to go to the demo part, and this was at 4 Bravo F Charlie 0. Again, let me scroll through here. So I see my IAT structure. So that means this EAX IAT structure. So I'll right click, do set equate. Then I'll do API enum and find first file, double click it, and it'll add it for me. So I scroll through, I see another one here. I'll just type E for shortcut, and then I'll type out API enum, and I see this is a wide character string compare. You can see now this is obviously going to take a little bit of work to label all these, but I can at least label them relatively quickly. And then as I go through here, so I see one more structure here, E for shortcut, API enum, and another string compare. And now I can start analyzing for functionality. That's really all we need to talk about today. I hope you enjoyed the video. If you did, please like the video below and subscribe to my channel so you get notified when new videos come out. I also love to know what you think about the video, so leave comments below. If you want more reverse engineering tips, follow me on Twitter. And if you're interested in more structured training, check out my website for the malware analysis courses I offer. Until next time, keep on practicing, try to learn something new every day.